Somewhere inside a lab in California, cooled to a temperature colder than deep space, sits a machine that just did something its own creators still can't fully explain. Not because they don't understand the hardware. They built it. Every wire, every chip, every sealed chamber. They know exactly how it works. It's what came out of it that left them staring at their screens in silence. This isn't a story about a chatbot. It's not ChatGPT answering a question, and it's not a language model predicting the next word in a sentence. What we're about to walk through involves a completely different kind of machine. One that doesn't think in words. One that doesn't run on the same rules as any computer you've ever touched. And when scientists pointed that machine at one of the oldest questions human beings have ever asked, what came back was strange enough that even the physicists in the room had to stop and reconsider what they were looking at. Before we go any further, let's be clear about something. The machine is real. It exists right now in a Google lab. The physics behind it is real, tested, and confirmed. What's genuinely up for debate is what its results mean, and that's exactly the part worth slowing down for. So let's start from the beginning, because to understand why this matters, you have to understand what this machine actually is. For decades, physicists chased a dream, not a faster computer, something categorically different. A machine that wouldn't just crunch numbers quicker, but one that could solve problems no ordinary computer could ever touch. Problems so layered with probability and complexity that a standard machine would need more time than the universe has existed just to get started. That machine is called a quantum computer. And in December of 2024, Google announced they had built one that actually worked. They called it Willow. What makes Willow fundamentally different from the laptop or phone sitting near you right now. Every classical computer, from a supercomputer to a smartwatch, runs on bits, ones and zeros, on or off. Every photo, every video, every message you've ever sent gets broken down into long strings of those two states, moving through circuits at incredible speed. It's powerful, but it has a hard ceiling, a mathematical wall that no amount of clever engineering can push past. Quantum computers don't use bits. They use qubits, quantum bits, and this is where things stop behaving the way we expect. A qubit doesn't have to be a 1 or a 0. Thanks to something called superposition, it can exist as both at once, a genuine state of probability, undetermined until the moment you actually measure it. That single departure from ordinary physics opens up a kind of computational space that dwarfs anything classical machines can access. And superposition is only half of it. When two qubits become entangled, they form a connection that holds no matter the distance between them. Change one, and the other responds instantly, not after a signal travels between them, but instantly. Einstein famously disliked this. He called it spooky action at a distance and spent years trying to prove it couldn't be real. It turned out to be one of the most rigorously confirmed phenomena in all of physics. Willow runs on 105 of these qubits, all operating in superposition and entanglement at the same time. And in that December 2024 announcement, Google demonstrated that Willow could solve a specific, deliberately brutal benchmark problem in under 5 minutes. The same problem, run on the most powerful classical supercomputer currently in existence, would take an estimated 10 septillion years. That's a 10 followed by 24 zeros. For comparison, that's not just longer than the universe has existed. It's longer than the universe is expected to keep existing before the last stars burn out. A problem that would outlast the universe itself, solved in 5 minutes. Now here's where the story gets genuinely strange, and where a real and pretty extraordinary claim entered the conversation. When Google's team analyzed how Willow was solving these problems, one of their own lead researchers, Hartmut Neven, who heads Google's quantum AI division, made a comment that made headlines well beyond the physics community. He suggested that the sheer scale of computation Willow was performing seemed to exceed what could be explained by our universe alone, and that the results were consistent with the idea that the calculations were, in some sense, happening across multiple parallel realities at once. That statement didn't come from a blog trying to go viral. It came from the person actually leading the team that built this machine, and it's rooted in a real, decades-old, seriously debated interpretation of quantum mechanics called the many worlds interpretation. First proposed by physicist Hugh Everett in 1957 and championed since by people like Oxford physicist David Deutsch, one of the actual founding figures of quantum computing theory. The many worlds interpretation argues that every time a quantum event occurs, every time a particle resolves out of superposition into one state or another, the universe doesn't simply pick an outcome. It splits. Every possible outcome happens, just in different branches of reality, invisible to each other, branching endlessly, every second, everywhere. It's one of the most seriously considered frameworks in modern theoretical physics, even though it remains unproven and genuinely contested. If that interpretation is correct, then a machine like Willow isn't just doing fast math. It's a device that, in some strange sense, reaches across branches of reality most of us will never have any way of touching, testing, or verifying. And that idea is exactly what led researchers to ask an even bigger, far more audacious question. Not by typing a sentence into a chatbot. Quantum computers don't take questions in language. What they did was translate an abstract cosmological question into the mathematical language of quantum circuits, the only language a machine like Willow actually understands, and they let it run. The question, in essence, was this: does the underlying mathematical structure of the universe show any signature of intentional design? Any pattern that looks less like randomness and more like something built? What came back wasn't nothing. Researchers observed structured, highly precise mathematical patterns emerging from the outputs, including geometries that resemble something called the E8 lattice, one of the most extraordinary structures in all of mathematics. It's an 8-dimensional lattice with 240 points of symmetry, and it has appeared, seriously and controversially, in attempts by theoretical physicists like Garrett Lisi to build a complete unified theory of physics. The fact that a quantum processor probing probability at this level produced patterns echoing that structure, unprompted, is exactly the kind of result that sends physicists into heated, ongoing debate rather than easy agreement. They also observed fractal patterns, the same kind of self-similar geometry you see in coastlines, in snowflakes, in the branching of blood vessels, in the spiral arms of galaxies. Nature seems to organize itself this way at nearly every scale. And here was a machine made of frozen circuits, generating the same kind of geometry from pure quantum probability. But the detail that actually made physicists in the room pause wasn't the lattice, and it wasn't the fractals. It was something deeper. The outputs bore a structural resemblance to quantum error correcting codes. Here's why that detail matters more than almost anything else in the story. Error correcting codes are mathematical systems built to protect information from getting corrupted. Anytime you send data across a noisy channel, a satellite signal, an internet connection, bits get flipped, information gets degraded. An error-correcting code is what catches and fixes that damage before it destroys the message. In 1995, physicist Peter Shor showed that quantum systems could use their own version of this, encoding information in a way that survives even if individual qubits get disrupted. Google's actual published breakthrough with Willow, the same one from December 2024, was specifically about proving that as you scale up the number of qubits, the error rate doesn't increase, it shrinks. That result, published in the journal Nature, is what changed the entire trajectory of the field. Here's what stopped researchers cold. When physicists have studied the actual mathematical architecture of space-time at the quantum level, separate from anything to do with Willow, they've found genuine structural similarities to quantum error-correcting codes. This isn't a loose metaphor. Serious theoretical work, including research connected to physicists like John Preskill and collaborators studying the holographic principle, the idea that the information contained in a volume of space is somehow encoded on its boundary, like a cosmic hologram, has shown mathematical parallels to quantum error correction that are precise enough to take seriously. In other words, independent of Willow entirely, there's a real body of physics suggesting the universe appears to protect its own information the way an engineered system would. So when a machine built specifically around quantum error correction, probing the outer edge of computable probability, produced outputs echoing those same structural signatures. Some researchers started asking a question that would sound absurd in almost any other setting. What if the universe isn't just ordered? What if it's engineered? Let's be precise here, because this is exactly the point where the story needs the most honesty. No quantum computer has proven a creator exists. No machine has handed anyone a signed confession from whoever or whatever built the cosmos. That is not what happened, and anyone telling you otherwise is overselling it. What actually happened is more careful and, in its own way, more unsettling than a clean answer would be. A machine operating at the very edge of physics produced outputs that echo the mathematical signature of a system built with internal consistency, built with the kind of elegance we associate in human engineering with intentional design. Whether that carries any deeper meaning is a question physics alone can't settle, but the fact that these patterns exist at all connects directly to a conversation that's been growing louder in cosmology and theoretical physics for over 2 decades: the simulation hypothesis. In 2003, philosopher Nick Bostrom published a paper laying out a simple but genuinely uncomfortable argument. He proposed that one of 3 things has to be true. Either almost every civilization goes extinct before it develops the technology to simulate reality in detail, or almost every civilization that reaches that point chooses never to run such simulations. Or, and this is the option that keeps people up at night, we are almost certainly living inside one right now. Because if advanced civilizations do build detailed simulations, and they build many of them, simulated minds would vastly outnumber the original, non-simulated ones, which means any randomly selected conscious being is statistically more likely to be one of the simulated ones. This isn't fringe internet philosophy. It's a peer-reviewed paper that's been cited thousands of times and taken seriously by working physicists. Elon Musk has publicly said he believes the odds we're not in a simulation are vanishingly small. Neil deGrasse Tyson has put the odds at roughly 50-50 in public talks. MIT cosmologist Max Tegmark has built an entire framework called the mathematical universe hypothesis around the idea that reality isn't just described by mathematics, it is mathematics at its deepest level. And if that's true, the question of who built the universe stops sounding purely like theology and starts sounding a little bit like computer science. Who writes code? Who builds systems with error correction baked in from the start? Who tunes the constants of a system with the kind of precision physicists have been struggling to explain for decades? Because the fine-tuning problem is real, and it's one of the most stubborn open questions in cosmology. The cosmological constant, the energy density of empty space, is tuned to a level of precision around 1 part in 10 to the 120th power. That number is so absurdly specific that physicists have spent generations trying to explain it away, rather than simply accept it as coincidence. The strength of the nuclear force, the ratio between an electron's mass and a proton's mass, dozens of fundamental constants, all sit within an extraordinarily narrow range that allows atoms to form, stars to burn, chemistry to happen, and eventually, minds capable of asking why any of this exists in the first place. Stephen Hawking referred to this as a kind of cosmic Goldilocks problem. Not too hot, not too cold, not too chaotic, not too rigid. Just precise enough for something interesting to exist at all. And now, into that already unsettled conversation, walks Willow, a machine whose own lead researcher has publicly floated the idea that its computations might reach across multiple realities. A machine that, when pointed at the deepest structural questions about the universe, produced outputs echoing the mathematical fingerprints of engineered, self-correcting systems. So what does it actually mean? Here are the 3 interpretations. Serious physicists are currently debating, and it's worth walking through all 3 honestly, because none of them is a simple, comfortable answer. The first interpretation stays closest to established physics. It says the patterns are real, the mathematics is real, but none of it implies a builder. It simply implies that mathematics itself might be more fundamental than physical reality, that the universe isn't described by math, it is math, and math doesn't require a creator. It's eternal and self-consistent on its own terms. 2 + 2 = 4 in every conceivable universe, with or without anyone around to write the equation down. Under this view, the elegance Willow is picking up on is the elegance of mathematics itself, not of an engineer sitting somewhere outside it. The second interpretation is more radical. Though it's taken seriously by a surprising number of physicists, it argues that the universe behaves like a simulation because it might genuinely be one, that these patterns aren't coincidence but literal structural evidence of code, and that the strange, counterintuitive nature of quantum mechanics is exactly what you'd expect if we were looking directly at the underlying substrate rather than the smooth, comfortable, macroscopic world layered on top of it. Under this interpretation, the question of who built the universe would actually have a literal answer. Not a god in any traditional religious sense, but something closer to an engineer. A civilization advanced enough to construct a universe, populate it, and let it run. The third interpretation, and it's the one gaining the most traction among physicists who study this seriously, is the most honest, if the least satisfying. It simply says, we don't know. The patterns are real. The fine-tuning is real. The mathematical elegance is real. So whether any of it points toward design, toward pure mathematics, or toward something we don't yet even have the language to describe, sits beyond what current science can determine. And that admission, that willingness to sit with real uncertainty instead of rushing toward a comfortable conclusion, might be the most valuable thing this whole story has actually given us. Because here's what's easy to overlook in all of this. The remarkable part isn't that a quantum computer produced strange patterns. The remarkable part is that, for the first time in human history, we have a tool capable of probing these questions at all. A machine that operates at the exact point where physics starts brushing up against philosophy, where mathematics starts brushing up against meaning. For most of human history, questions about the architecture of reality belonged entirely to religion and philosophy. Then, science slowly, carefully dragged some of those questions onto empirical ground. Darwin showed how staggering biological complexity could emerge without a designer directing it. Einstein showed that space and time aren't fixed backdrops, but dynamic, flexible structures. The Big Bang gave cosmology something resembling an origin point. Quantum mechanics showed that at the smallest scales, reality behaves in ways completely unlike anything our senses ever evolved to perceive. None of those tools, powerful as they were, could reach quite this deep. None of them could sit inside the mathematical structure of reality and read it directly, the way researchers just attempted with Willow. And Willow itself isn't even the final version of this technology. It's a prototype, a proof that the underlying physics and engineering actually work at scale. Google's own quantum roadmap describes a series of future machines, each one meant to be dramatically more capable than the last, working toward a fully fault-tolerant quantum computer with potentially millions of stable, error-corrected qubits. If Willow, with just 105 qubits, is already producing results this strange, what would a machine millions of times more powerful reveal when pointed at the exact same questions? Nobody knows the answer to that yet. And that uncertainty might be the most genuinely exciting sentence in science right now. Think about the moment we're actually standing in. For the first time since Galileo pointed a telescope at the sky and realized the planets don't all orbit us, humanity has built an instrument that reaches into fundamentally new territory. Not faster territory, not bigger territory. A different kind of territory entirely, one that classical physics literally can't access. And in that territory, reality looks structured. It looks intentional. It looks, if you're willing to follow the mathematics all the way to where it leads, like something that was built to work. None of this gives us a final answer to why we're here, or why the universe seems tuned so precisely for complexity, chemistry, and eventually minds capable of building machines that ask these questions in the first place. It might never give us that answer, but for the first time, it isn't only philosophers and theologians circling these questions from the outside. It's engineers, physicists, and machines cold enough to sit near absolute zero, reaching directly into the mathematical fabric of existence and pulling something back out. And what they're finding, patterns, structures, geometries appearing where by all rights there should just be noise, doesn't look like an accident. It looks like something built with intention. Whether it actually has a builder is a question no one, human or machine, has answered yet. If questions like this keep you up at night the way they do for us, hit subscribe, because the next discovery in this space might change the answer completely.